All right, this is MA 161's Fall 2022 Exam 2. So this is, I think, going to be the earliest or latest Exam 2 that I'm doing for Calc 1, the one from Fall 2022. So if this is your first Exam 2, then hi, hello, welcome. There's going to be a lot of derivatives ahead. We're doing a lot of things like figuring out, the maximum height that a ball reaches once you throw it upwards and things like that. So lots of product rule and chain rule and things like that. So, question one is a perfect example of that. So, suppose you throw a stone upwards with an initial. Okay, it's just reiterating a lot of things from the position function that it gives you. So what this means is if you plug in a value like 3 in for all these t's, whatever value that's going to give equals whatever it's going to be, that's going to be the height of the stone 3 seconds after you throw it. So that's what that means. We're asked to, knowing that, we're asked to find the height of the stone at its highest point. So whatever it is, when we throw it up and then it, eventually comes back crashing down to Earth, we have to find that height, whatever it is. So I think the best way, or maybe the only way of figuring out this problem with calculus is, so first off, we have our original position function, s of t. That's probably going to be some parabola where we have our peak there. It starts out, you throw it with an initial velocity, hits its peak, and then eventually comes crashing down back to Earth. We're asked to find that maximum height here for whatever t seconds after you throw it. What you can do to find that point there is you can take s prime of t, the first derivative of t. Now, since s of t is the position function, when you take s prime of t, the derivative, you're going to get the velocity function. So when you find the velocity, most often that is going to be a straight line going downward, the velocity function. And what's even cooler is that this point here, where the slope intersects with the x-axis, that is going to be the exact same t value as the peak here. So those 2 points correspond to one another, and we can use that to our advantage. What we can do is we can find out the first derivative of s of t, and that'll be, whatever it ends up being, and we can set that equal to 0, because here this is the same as 0. So we can set it equal to 0 there, and at that point we'll only have one variable to worry about, and we can solve for that variable. And what that variable is going to be our critical points, which is the points where x either, or where t in this case, hits either a maximum or a minimum. So that's the big picture for this problem. Now to go ahead and actually do it, first off we need to find out what that derivative is. We need to take the derivative of s of t. Now, this might be your first derivative, or maybe not. I think there might have been a couple in the exam ones, but in any case, I'll go a little slower for this. So when you do derivatives, you go term by term. So we're going to have to do 3 sort of partial, no, I should not say partial derivatives. That's its own thing. You'll do 3 separate derivatives here. So first, finding the derivative of 32. The derivative of any constant, which is some term that doesn't have any associated variable with it, is just going to be 0. So you've got s prime of t. That's going to start out by just being 0. And then plus, now we got to do the derivative of 64t. So when we do 64t, this is the same as 64t to the first power. We're going to use the power rule. So we're going to take this exponent here, move it out to the front, and then reduce it by 1. So in this case, our exponent is 1, so we're going to bring a 1 out to the front. It's going to be 1 times 64 times t to the 1 minus 1 is the 0th power. So in this case, we've got 1 times, which is nothing, 64 times t to the 0, which equals 1, and 1 times 1 is nothing. So we're just left with 64 here. So you've got 0 plus 64, and then we find out the derivative of negative 16t squared. So now we have the negative 16t squared. We're going to do the same thing. We're going to take that 2, move it out to the front, and then reduce it by 1. So we're going to have 2 times negative 16 times t to the 2 minus 1 is the first power. So this is going to be 2 times negative 16 is minus 32 times t to the first power. And that is our derivative. We can forget about the 0. So we're going to rewrite that over here. 64 minus 32t is our first derivative of the position function, which, by the way, equals the velocity function. And now we can go ahead and set this equal to 0 and solve for t. So 0 equals 64 minus 32t. So solving this, looks like we can subtract 64 from both sides. Negative 64 equals negative 32t. Dividing both sides by negative 32, we get 2 equals t. So we've got this now, t equals 2. So we know that 2 seconds after you throw it, the stone is going to hit a critical point, aka it's going to hit a maximum or a minimum. Now, in the context of this problem, it doesn't make much sense if your stone starts to, rise upwards on a normal planet. That wouldn't really happen. So we can basically forget about that. We're going to have a maximum, which is exactly what we're looking for. We're looking for the highest point. So we're on the right track here. Now what we can do is we have our t value. We've got 2 seconds after takeoff. So we can just go ahead and plug 2 back into our position function to find that height that we're looking for. So doing that, we get s of 2 equals 32 plus 64 times 2, 62, minus 16 times 2 squared. Evaluating this, it's going to be 32 plus 128 minus 64. And then solving this, we get 32 minus 64 is negative 32. 128 minus 32 is 96. So 96 feet. So that means that 2 seconds after you throw it, the stone is going to be 96 feet in the air, and that's going to be its peak here. That's going to be the highest height that the stone will reach. All right, question 2. Suppose we have f of x here, which equals x times e to the negative x. If big M is the absolute maximum of f on the interval from 0 to 2, and little m is the absolute minimum on that same interval, what's the sum big M plus little m? So we need to find the absolute maximum and absolute minimum of f of x. And to find those, we're going to need to find f of x's critical points, which are the points where f of x either has some peak or some valley at those points. And to find those critical points, we need to take the derivative of f of x. We need to find the derivative of x times e to the negative x. So to take the derivative of that, it's not going to be as simple as just a one and done like power rule or maybe another step with a chain rule or something like that. We are going to need to use the product rule here because we have 2 x terms that are being multiplied together. We've got an x on the left and an e to the negative x on the right. Both those terms have an x nested somewhere within it. So what we can do is we can use the product rule, which states if we have something in the form of a times b, in this case a is x and b is e to the negative x, when we take the derivative of that, there's a template we can use where it's a prime b plus a b prime. So if we were to just fit x and e to the negative x into a and b and follow this sort of formula, taking derivatives wherever there's a little prime symbol here, we'll get the derivative of f of x. Makes it pretty easy for us. So taking the derivative now, f prime of x, that equals first a prime, that's the derivative of x, which is 1, times b, which is e to the negative x, plus a, which is x, times b prime, that is the derivative of e to the negative x. Derivatives of powers of e are pretty simple. They're a lot better than derivatives of any other power. You just rewrite the original statement, which is e to the negative x. Take the derivative of the exponent, so derivative of negative x is negative 1, and then just put that out in the front. So multiply everything by that. So we're going to multiply e to the negative x by negative 1. So there we go. We have our first derivative of f of x now. Let's since we're going to have to do more things with this, we're going to set it equal to 0 and solve for x and stuff. Let's make it a little easier on the eyes and simplify a little bit. So multiplying things out, we're going to have e to the negative x minus x times e to the negative x. And then we can actually go one step further. We can take out an e to the negative x, since it's in all of these terms here. That'll become e to the negative x times 1 minus x. So that is f prime of x. So there we go. We have a simplified first derivative of f of x. Now, to find our critical points with this, we can set it all equal to 0 and solve for x. So 0 equals e to the negative x times quantity of 1 minus x, and solve for x. So to solve, it looks like we've got two x terms being multiplied together. So what we can do to solve for x is split it into two separate equations now. So we've got 0 equals e to the negative x, and 0 equals 1 minus x. And the solutions for both equations will be the combined solutions for our original equation. So I would like to start with the right equation here because it looks far simpler. Let's just ease into it a little bit. So we can subtract 1 from both sides. You got negative 1 equals negative x, and then flip the signs of both sides. So we got 1 equals x. So there we go. We've got our first critical point, which occurs at x equals 1. And again, what critical points mean is that it occurs at either a valley or peak of f of x. So when f of x equals 1, it's going to be a local maxima or a local minima, or an absolute maxima or an absolute minimum, but we don't know yet. It's just a critical point. So we've got our first critical point. Now to do this one, we might have a problem here actually, because what powers of constants mean, so we've got a power of e here, that always just looks like, assuming there's not like a minus 2 or something on the end of it, which there isn't, what that looks like is this, where it grows on the right. It grows all the way up to infinity on the right, but on the left, it just slowly gets closer and closer to the x-axis, but never touches it. So it gets closer and closer to 0. The limit approaches 0, but it never equals 0. And that's a problem since we're trying to set this equal to 0. So in this equation, actually, we have no real solutions, which kind of, it might be an issue for this problem because we're trying to find both a maximum and a minimum. So you'd think we need at least two critical points to work with so we can find which one is a maximum and which one is the minimum. So you might think we're screwed, but fortunately we aren't, because this is a slightly different type of problem. It's just asking us for the maximum minimum within this range. So imagine if we have a big parabola that looks like this. Obviously here we've only got one critical point. We've got a minimum right at the bottom, and there's really no maximum that we can find. But say it was kind of a similar problem and we just restrict it to within a certain range, like say it's this range here, we kind of do have a maximum now. It's going to be either one of these points. We can just figure out which one is bigger, and hey, there you go, that's our maximum. So that's the same thing here. We've only got one critical point, but we can still find the other. So the critical point is either going to be a maximum or a minimum. So we can find whatever the minimum or the maximum is by just comparing the evaluations of the two endpoints and go from there. So I'm kind of just not realizing that was a lot of words and not really any math to back it up, but we can go ahead and figure that out now. What we can do is just figure out what f of 0, f of 1, and f of 2 are, and we can sort of determine based on what these values are if f of 1 is the minimum or the maximum, and b, which one of these two, f of 0 or f of 2, we should take to be the other minimum or maximum. So doing all that now, f of 0 is going to be, all right, 0 times e to the negative 0, that's just 0. F of 1, that's going to be 1 times e to the negative 1, that's the same as 1 over e. And f of 2 is 2 times e to the negative 2. That's the same as 2 over e squared. So we have all of our evaluations now Um, I'm kind of feeling like I messed something up because these are supposed to sort of. Oh, no, I didn't. Okay, I did not mess anything up because these follow a pattern, kind of. So this is the biggest value that we have here. It's kind of hard to notice because it's got like e's in the denominator and stuff. But if you were to punch this into a calculator, 1 over e is greater than 2 over e squared. And 1 over e is also greater than 0. So because of that, we can kind of infer that 1 over e is our maximum here. This is a maximum here, this critical point. And that means one of these must be our minimum. In this case, it must be 0. 0 is clearly smaller than 2 over e squared. So there we go. We've got our minimum and we've got our maximum. So now all we have to do is add them. So 0 plus 1 over e is 1 over e. And that's how we find big M plus little m. So this was a weirder problem because it started off pretty simple, just finding absolute minimums and maximums, which is critical point nonsense. But we had to sort of adapt on the fly because we didn't have as many critical points as we thought we'd need, and we had to figure out which one of those endpoints had to be the other minimum or maximum. And we did end up doing that, and we found our answer, which is wonderful. Question 3, this is just a limit problem. So the limit as x approaches 2 of this fraction here. So I feel like there's some special way you can find limits of this this trig function here, this sine. But honestly, I kind of don't like the ways that they teach you. I personally don't like it. It's a fine method, and if you're comfortable with it, then go ahead. But I think I'd be more comfortable with using L'Hopital's rule here. So we can use L'Hopital's rule because if we were to plug in this 2 for these x's, which would become sine of 2 minus 2 all over 2 squared minus 4, which equals 0 over 0. This is an indeterminate form because it's 0 over 0. And because of that, we can use L'Hopital's rule. Now, what L'Hopital's rule means is that you can take the derivative of the top and the bottom, and your limit will not change. So after we do these derivatives, the limit will still approach the same value. So if we do these derivatives, usually things will start canceling out, or you can just plug in that value that approaches and it won't be dividing by 0 or anything, and you'll get an actual value, an answer. So we can go ahead and do that, take the derivative of the top first. So derivative of sine is just cosine, so this is going to be cosine of x minus 2. Now because we have something interesting in the middle, it's not just an x, we do have to apply the chain rule, which means that we multiply this whole thing by the derivative of the inside. So the inside is x minus 2, the derivative of x is just 1, and the derivative of negative 2 is 0, because it's just a constant. So that didn't end up changing anything, we just multiplied everything by 1, but still, we had to make use of the chain rule there. And then all divided by derivative of x squared. When you take out the 2, put it in front, that becomes 2x. And you reduce that power by 1, so the new power is 1. And then negative 4, again, that's just a constant, so that just becomes 0, and that's its derivative. So now I've got the derivative of our original function, our original fraction there. And it looks like if we plug in that 2, everything will work out. If we do cosine of 2 minus 2, so cosine of 0, that equals 1, and 2 times 2 is 4. So the limit as x approaches 2 is 1/4. So that was a quick little L'Hopital's rule problem. Just check if you have a 0 over 0 form, an indeterminate form. And if you do, you can take the derivative of both the top and the bottom, and then usually it'll work out after that. And if it doesn't, you might have another indeterminate form, and you can use L'Hopital's rule again. You can use it as many times as you want, which is cool. Okay, question 4. A 5-foot ladder is leaning against the wall when Jack begins pulling the foot of the ladder away from the wall at a rate of 0.5 feet per second. how fast is the top of the ladder sliding down the wall when the foot of the ladder is 4 feet from the wall? All right, that was a lot of words, and I barely even understood all of them. So let's go ahead and draw this out visually instead. That'll make it a lot easier. So we've got our vertical wall here and a floor, and we've got some ladder leaning against the wall like that. This is our ladder. So notice that this ladder, it makes a really nice right triangle with that wall and the floor. So it'd be pretty helpful if we had variables to correspond to all these sides, x, y, and z. So we've got the top of the ladder and the base of the ladder, and we've got this crook here, this jack fellow is pulling the base of the ladder away from the wall at a rate of 0.5 feet per second. So he's doing that. It's moving, the base is moving at a constant rate. It's growing. X is growing at a rate of 0.5 feet per second. And once x equals 4, then y is going to equal what? It's going to equal some rate, and it's going to equal some length. And we're asked to find that rate. How fast is the top of the ladder sliding down? So we're trying to find that rate that it's moving down. And side note, z also technically has a rate that is moving, but its rate is 0 because we're not like, chopping the ladder in half or anything. We're not changing the size of the ladder. So the rate at which z is changing size is 0, and that actually will be helpful later on. So we've kind of visualized what this problem looks like now. We're asked to find the rate at which y is changing, essentially. And to find that, we can use our good old friend, the Pythagorean theorem, which again is x squared plus y squared equals z squared. So this is relating all of the lengths of this triangle together, x, y, and z. It's relating all the heights and the widths and the lengths there. But we need to find the relation among all of the rates. We are given a lot of these rates. We're given the rate at which the base of the ladder is moving, and we can also figure out the rate at which the ladder itself is moving, and we're trying to figure out the rate at which the top of the ladder is moving. So there's actually a really simple way to get an equation from the Pythagorean theorem that relates all of these rates together. The related rates, that's what these problems are called. And what we can do is just take the derivative of all of this. We can take derivatives of x squared, y squared, and z squared and get a new equation from it. So if we do that, we get 2x times dx over dt. Make sure to remember these dx's here. Plus 2y over dx over dt equals 2z times dz over dt. I'm sorry, these are actually all supposed to be, dx, dy, dz here. So there we go. We have a new equation. This actually still holds true. No matter what variables these all equal, it's going to always be equal to each other. Like they're all going to check out like that. That's the cool thing about the Pythagorean theorem and related rates. And now the cool thing is we have these dx, dy, dz's over dt's, which represent these speeds that these ladder points are moving at, that x, y, and z are growing by. So since we have those integrated into our equation, now we can use them to figure out what dy over dt is. That's what we're trying to find. And the cool thing is that these other variables here, x, y, z, and dx and dz over dt, are either given to us in the original problem, or we can figure them out on our own. So once we have all of the other variables, we'll only have one variable left, which is the dy over dt, and we just solve for it, and that'll be our answer. So plugging in all of these other variables now, first up we have x, which is the length of the base of the ladder, which in this case is 4 feet. That's what we're trying to evaluate this at when the base is at 4 feet long. Dx over dt, that represents the rate at which the base of the ladder is changing. This says it's at 0.5 feet per second, so half a foot a second. And then plus 2, y is the height of the ladder at this particular moment. It doesn't actually give us that. We're trying to figure out what that is, and it's not stated in the original problem. But to find it, we can just use the original Pythagorean theorem, which relates all those lengths together. Because we're given x, it's 4, and we're given y, or z, which is 5. So if we do, let's do it over here, 4 squared plus y squared equals 5 squared. We can do Pythagorean theorem stuff and figure out what y is. So if we subtract 4 squared from both sides, we get y squared equals 5 squared minus 4 squared. That's 25 minus 16, which is 9. And if we square root both sides, we get y equals 3. So that must be the height of the ladder at this particular moment where the base of the ladder is 4 feet. So this is now 3. Then we have our original dy over dt. That's what we're trying to find. And then we've got 2z times dz over dt. But the cool thing is, we don't really have to figure out any of this because this dz over dt is 0. Because dz over dt represents the rate at which the ladder itself is changing size, the rate at which z is changing. And it isn't changing at all. The ladder isn't being stretched or compressed or anything. We're not chopping it in half. So dz over dt is 0. So this entire right side is now 0. So now we see we only have one variable in this entire equation. So we should, our mathematics brains should be immediately pivoting towards, okay, we should solve for that variable. So we need to solve for dy over dt. So now combining all these variables together, looks like we can get 4 plus, that would be 6 dy over dt equals 0. We can subtract 4 from both sides to get 6 dy over dt equals negative 4, and then divide 6 on both sides gives us dy over dt equals negative 4/6, which is 2/3. So that is our answer. And that makes sense that the answer is negative because, well, if the ladder is sliding out from the wall, it means that the top of the ladder is going to be moving down the wall. Since as the right moves outwards, the top must be moving downwards, which makes sense. All right, this question sucks. I'm going to come around and say that just because there's a part in it that just requires some raw memorization skills. You have to remember what the derivative of inverse tangent is, which, if I'm thinking correctly, inverse tangent of x, taking the derivative of all that is 1 over 1 plus x squared. You kind of just have to remember that, as well as all of the other derivatives of trig functions, like at least sine and cos and tangent. So yeah, you're gonna have to kind of remember that for this problem. So actually doing the problem now, find the slope of the tangent line to the curve y equals x tangent inverse tangent of x. Yeah, this is just a derivative problem, and then at the end we're gonna plug in 1 into it. So yeah, doing this now, it looks like we're gonna need to use the product rule because you've got x times inverse tangent of x. Both of those terms have an x nested somewhere within it. So we need to use the product rule, which states if we have something in the form of a times b, derivative will give us a prime b plus ab prime, where a is, in this case, x, and b is inverse tangent of x. So if we were to plug in all of those values for a and b, we'd get our derivative of the full function. So y prime is now a prime is derivative of x, which is just 1, times b, which is inverse tangent of x, plus a, which is just x, times b prime, so the derivative of inverse tangent of x. As we've remembered and as I've stated, derivative of inverse tangent is 1 over 1 plus x squared. That's kind of, yeah, I wish they didn't require this from this much memorization. I wish they would let you use some formula sheet on these exams, but they don't, so I guess you just kind of got to remember this stuff. So anyways, we now have our full derivative here. We now have our y prime. So now we can just go ahead and plug in the x value that it wants us to evaluate it at, which in this case is 1. So we can go ahead and figure this out. So, excuse me, my throat is getting a little raw. So we've got 1 times, we don't need to keep that around, it's just 1. We've got tangent or inverse tangent of 1 plus 1 times 1 over 1 plus 1 squared. That's a lot of ones. Anyways, all right, this is the hardest part of this whole thing. Inverse tangent of 1. If I'm not mistaken, if I'm thinking about it correctly, that's going to be pi over 4, because if you have our unit circle, that's actually a bad representation because of what I need to do. If you have a unit circle, tangent is just whatever the length of this line is. So if you draw the tangent like this, where you have this big line that forms this right angle with the line angle in the middle that you're trying to evaluate at, tangent is just the length of this line. And in this case, whenever it equals 1, we're doing inverse tangent, so we need to go the other way around. If this length is 1, then that means this length also has to be 1, because this is a right angle. So I'm pretty sure it's pi over 4, because this angle is pi over 4 plus, and then it's all of this. So it's 1 times, which is still just 1, and it's 1 over 1 plus 1 squared, which is 1/2. So pi over 4 plus 1/2 is B. So there we go. That's the answer to this problem. So the fun part was using this unit circle. Personally, I really like unit circle stuff. I don't know what it is about it, but just like seeing all these things graphed out visually with this circle and all these angles, it always gets me excited. What I do not find exciting is memorizing this stuff. Again, I really wish they would let you take some of these formulas in with you, or just give you a pre-made formula sheet. I remember that's what my teachers did in high school, but they don't let you do that because math department is interesting sometimes. So just remember your derivatives of inverse trig functions, and you should be fine for these types of problems. Okay, I did all the work for this problem and did it 99% correct, but I changed a minus to a plus, and it got me a wrong answer that just so happened to be this answer choice right here, A. So that is not the right answer, spoiler, but here I know what I did wrong now, so I'm going to do it right this time. I know I am. So this problem 6, it's just a derivative problem. So we have an f of x equals natural log of 2x plus 1 all over x minus 1, and we're asked to find its derivative and then plug in 2 into that derivative. All right, so first step for this derivative, it looks like this natural log is superseding everything, and that's probably going to be the thing we have to take the derivative of first. So derivative of natural log is actually pretty easy. When you have a natural log and you take the derivative, that's just equal to 1 over x, 1 over the inside. So fitting that to our problem, that's going to be f prime of x equals 1 over, and then 2x plus 1 all over x minus 1. So we're not quite done yet, though. We have to take this one step further. Since this inside was not just an x, it's a big fraction, we have to apply the chain rule. So we have to multiply all of this by the derivative of the inside, which was 2x plus 1 all over x minus 1. So now we have this. This is technically our derivative, but we have to go one step further because we have to figure out what this derivative is now. So doing that, f prime of x equals, well, actually first we can go ahead and condense this too. 1 over a fraction is just the same as the reciprocal of the fraction. So this is now x minus 1 all over 2x plus 1. And then times, all right, our original derivative here. Looks like we have the derivative of a fraction. And what you can do for derivatives of fractions is the quotient rule. So the quotient rule states if you have something like a over b that you want to take the derivative of, so in this case a is 2x plus 1 and b is x minus 1. When you take the derivative of that, there's a nice formula you can use. It's kind of like the product rule, where it's a prime b minus ab prime all over b squared. So we can just fit that to our problem and we'll have our derivative. So a prime is the derivative of 2x plus 1, which is 2. b is x minus 1 minus a is 2x plus 1 times b prime, which is the derivative of x minus 1. That's just 1. All over, that's a bad line, just cut through everything. All over b squared, which is x minus 1 squared. So there we go. We have our f prime of x now. What I recommend doing for all of these derivative problems is if you don't have to really do anything after this step, like once you find your derivative, if all you have to do after this is just plug in the value or something, don't simplify this at all. Like just keep it as is, because if you simplify it, it'll look nicer, and when you go and plug in the value, it'll be easier. But it'll make your problem more error prone. You'll probably have a higher chance of getting the wrong answer in this question. So I wouldn't recommend multiplying everything out. Just keep it as is for now. So when we go ahead and plug in that value for f of 2, actually, we're going to go ahead and get 2 minus 1 all over 2 times 2 plus 1 times 2 times 2 minus 1 minus 2 times 2 plus 1 times 1 all over 2 minus 1 squared. So there we go. We just have to add, subtract, and multiply our way to the end now. So f prime of 2 equals, this will be 1 over 5, 1/5, times, so this is going to be 2 times 1 is 2, minus, this will be 5 times 1, which is 5, all over, this is going to be 1 squared, which is just 1, and this is going to equal 1/5 times -3, which is -3/5. So there we go. Pretty vanilla derivative problem. It used a couple key derivative, cases. What do they call them? Like these things, just derivative properties, things you can use to make derivatives a lot easier. Looks like here is derivative of natural logarithms and the quotient rule. Those are two key ones, along with the chain rule and product rule and power rule and things like that. So these are two good ones to keep in the back of your pocket when doing these derivative problems. All right, question 7. We're halfway done with this exam. Let h of x equal f of x plus 4g of x, where the graphs of f of x and g of x are shown in the picture. Find h prime of 2. So find the derivative of h and then plug in 2 for it. All right. Okay, I think the best way we could do this problem is that based on the visualizations of the graph here, we can actually figure out the exact equations of f of x and g of x. It looks like they're just straight lines, so you can use things like rise over run to figure out the slope, and the y-intercepts to figure out the plus b, the mx plus b. So reiterating all that, any function that's just a straight line has the form mx plus b, where m is the slope and b is the y-intercept. And to find the slope, we can just take 2 points on the curve and figure out its rise over its run. So in this case, for g of x, this is going to give us, so if we have a g of x, the slope here is going to be 3 over 2. So 3 halves x, and it looks like its y-intercept is -1. So g of x equals 3 halves x minus 1. You can do the same thing for f of x. So it looks like here, actually, let me keep that up, 3 and 2. For f of x, it looks like it goes maybe here and here. So it looks like that's just 1 over 1. So this is going to be just x, and then its y-intercept is 3, so plus 3. So f of x equals x plus 3. So there we go. We have our f of x and g of x. Now we can just plug both of those into f of x and g of x up in the h of x equation and figure out what h of x is. So h of x equals f of x, which is x plus 3, plus 4 times g of x. So 3 halves x minus 1. Multiplying all this out, we'll get h of x equals, let's see, x plus 3 plus 4 times 3 halves is going to be 6x, and then minus 4. And then multiplying this out further, it gives us 7x minus 1. So that's what h of x is, and then to take its derivative, this is a pretty easy derivative. Just remember, you take out the power, you put it out front, so this is now 1 times 7x to the 1 minus 1 is the 0th power, x to the 0 is just 1, and so is this one, and this constant here just becomes 0. You can drop it when doing derivatives, so h prime of x is 7. So there we go. We have h prime of x, and when we plug in 2 for it, there are no x's left in the equation, so h prime of 2 is still 7, and that is our that is our answer. So there we go. This is a fairly well, you still have to do a derivative at the end of it, so it's still at the calculus level, but most of this problem was just like algebra stuff. It was y equals mx plus b. It's pretty refreshing. I kind of miss using that kind of stuff after all this, chain rule and limit, the one-sided limit, things like that. So sometimes it's nice to get like kind of a break once in a while. Question 8, another derivative problem. So we have f of x equals e to the power of tangent of 3x. We have to take its derivative and then plug in 0. So derivative of e to the tan 3x. First step is probably taking the derivative of this e here. That's the first thing that we're doing here. And derivatives of powers of e are super simple because it's the exact same thing. And then maybe chain rule after that, which we are going to have to do here. So when we're doing this, f prime of x is going to start off with just being e to the, it's going to be start off being the exact same thing, so e to the tan of 3x. Now we do have to do chain rule after that. We have to multiply by the derivative of tan 3x, but it was nice starting off with just like the exact same thing there. So now we have to figure out what the derivative of tangent of 3x is, and I guess you could figure this out by realizing that tangent is just sine over cosine. So you could rewrite this as sine 3x over cosine 3x, and then do probably the quotient rule after that. But there's an easier way. It's just remembering that tangent or taking the derivative of tangent is just going to make it secant squared of the original. So that's an easier way of doing that. 3x. Could do that. And then we do have to do another chain rule. We have to multiply by the inside, or the derivative of the inside, which is 3x. And the derivative of that is just 3. So there we go. We have our full derivative now. Plugging in 0 gives us, let's see, e to the tangent of 3 times 0 of all that, times secant squared of 3 times 0 of all that, times 3. So evaluating all this, we get e to the tangent of 0 is just 0, times secant squared of 0. So secant of 0, I actually don't remember off the top of my head, but what we can use is secant is just 1 over cosine. So this is the same as 1 over cosine squared of 0 times 3. And now this all equals e to the 0 is just 1. Cosine of 0 is also just 1, so it's 1 over 1, which is 1, times 3. We're left with 3. That's the answer. Is it? Hang on, let me double check here. 8 is A. Okay, wonderful. So yeah, derivative problem, we had to do derivative of powers of e, which is simple because it's the exact same thing, and the derivative of tangent, which is secant squared. So those are the two things that I'd recommend remembering for this problem. Question 9, another derivative problem. So f of x equals 8x all over e to the x plus x squared. We got to take its derivative and then plug in 0. So derivative of this, I think starting off, we got to do the quotient rule since we have a fraction here. Now restating this, the quotient rule is if you have a over b, you want to take its derivative, that equals a prime b minus ab prime all over b squared. So in this case, a is 8x and b is e to the x plus x squared. So we can use those and fit it to this template, and we'll have our derivative. So f prime of x equals, let's see, a prime, that's the derivative of 8x, so that's going to be 8, times the derivative of the bottom, or no, not the derivative of the bottom, just the bottom, so e to the x plus x squared, and then minus the top, which is, or a, which is just 8x, and then the derivative of the bottom, b prime, so derivative of e to the x plus x squared. All right, so this is going to be the derivative of e to the x, which is still just e to the x, plus the derivative of x squared, which is 2. So that's our top, our numerator, and then on the bottom we just have b squared. We have e to the x plus x squared, all squared. So there's our first derivative. Again, I'm going to restate that I don't recommend simplifying this at all, since all we have to do after this point is just plug in a value for x. I don't recommend simplifying because you can make another mistake when you do that, so I don't recommend it. So when we do f prime of 0 at this point, we get 8 times e to the 0 plus 0 squared minus 8 times 0 times e to the 0 plus 2 all over e to the 0 plus 0 squared all squared. So when we evaluate this now, we get, let's see, 8 times, let's see, e to the 0 is just 1 plus 0, so 1 minus 1, or not even, oh, all this is going to be 0 because this is a 0 and then this is going to be whatever, but that's all going to cancel out because of that 0 there. So this is now 8 all over, let's see, 1 plus 0 squared, which is just 1. So our answer is going to be 8. Double check I got the right answer. 8, wait, which one are we on? 9. 9 is D. Okay, awesome. So derivative problem that we had to do, started off the quotient rule, and we also had to remember our derivative of powers of e, which is super easy. You just restate the original problem. It's the exact same. And then that was really it. That was not too bad of a derivative. Question 10, another derivative question, but it's a little bit harder because the function that it gives you, the equation that it gives you, is pretty difficult to get it in terms of y. Like it would be really difficult to get this whole thing in a form where it's y equals something that has a bunch of x's in it. Like it's really just because of this cosine here. If that cosine wasn't there with that nested y, this wouldn't be too bad. We could just get this y all by itself and then do like a normal derivative. But we can't really do that. So instead, this problem looks primed up for implicit differentiation. So implicit differentiation is essentially where you just kind of take the derivative of each term by itself. And if you ever take a derivative of something with a y within it, you multiply it by dy over dx. And then at the end of it, you end up putting this all by itself on one side, and then that on the other side is the answer. So that was a lot of words. It's not as complicated as I just said it there. It's easier if I just show it out to you, and you'll probably pick it up. So if we were to take the derivative of this, 2 cosine of xy, looks like we'd be taking the derivative of cosine first. Derivative of cosine is negative sine, so this is going to be negative 2 sine of xy, and now we do have to do the chain rule after that, since the inside, let's multiply that by the derivative of the inside. So xy prime, we'll figure that out later, equals, now derivative of y squared is 2y, but since this had a y within it, since that had it's y squared, it's a y term, we have to multiply this term by dy over dx. And we're just going to keep it there. We're going to leave that there and treat it as like a third variable. And then this minus 1 term, derivatives of constants are just 0, so we forget about it. So we are almost done with our derivative. Now we have to figure out what this is, derivative of xy. Probably going to use the product rule for that. If you don't remember, product rule, if you have something in the form of ab, you want to take the derivative of it. That's equal to a prime b plus ab prime, where in this case a is x and b is y. So Derivative of, so a prime, which is the derivative of x, is 1 times b, which is y, plus a, which is x, times b prime, which is the derivative of y. Derivative of y is 1, but we just took the derivative of a y term, so we have to multiply this by dy over dx. And then now we're done with that, so it's just equal to 2y times dy over dx. So there we go. We have our full derivative now. Now what we do at this step, you could do one of two things. You have to do both of them at some point. It's really just up to preference. You have to plug in the two values here, this one for x and this one for y, into all of these x's and y's. You can either do that now and then solve for dy over dx, or you can start by rearranging this whole equation into a, like at the start, you can rearrange it to where dy over dx is on one side. I find it a bit easier to just go ahead and plug in the points right away and then crunch everything down, and then it'll be easier to get dy over dx all by itself, but you can do it either way. It just depends on what you want to do. Looks like I accidentally erased some stuff. All right, so I'm going to plug in the points. Pi over 2 for x and 1 for y, so negative 2 of sine of, let's see, x is pi over 2 times 1, and then all that times 1 times y, which is also 1, plus x, which is pi over 2, 1 dy over dx. We're going to leave that as is. Eventually, that's going to be the only variable here, and that's exactly what we're going to solve for when we're trying to find our derivative. So then that equals 2 times, y, which is 1, dy over dx. And there we go. So now we can multiply everything out and get these dy over dx's all by themselves. So, and that'll be our answer. So let's see, we can multiply this. No, actually we can divide both sides by 2, since there's a 2 being multiplied by everything on both sides. So I'm just going to erase those. And now we have, let's see, we can multiply this negative sign through. That would be easier if we multiply it into this negative sign term. So that would be negative sine of pi over 2. And now this inside part we should probably take care of, a lot of things being multiplied together. On the left side is 1, and on the right side is pi over 2 times 1 times dy over dx. So that's going to be pi over 2 times dy over dx. That is a messed up looking pi. There we go. And then all equals dy over dx. Now multiplying the sine, or the negative sine of pi over 2. Oh, actually we can simplify that. So sine of pi over 2 is just 1. So on this left side is negative 1, which is just negative, and that's negative 1 plus pi over 2 dy over dx equals dy over dx. Now we can multiply the negative sign through to both of the terms on the right. This is going to be negative 1 minus pi over 2 dy over dx equals dy over dx. We're almost there. Looks like at this point we can start getting these dy over dx terms all on one side and everything that isn't on the other side. So let's see, we can subtract dy over dx from both sides. So that'll leave us with negative 1 minus, so it'll be negative 1 minus pi over 2 dy over dx minus dy over dx. And that would combine to be, I don't know why I'm blanking it so bad right now, but let's just leave it like that. On the other side, let's actually add 1. So let's put a 1 on this side. This one gets dropped. You can take out a dy over dx on the left, so this is going to be dy over dx times, it'll be negative pi over 2 minus 1 equals 1. And then we can divide both sides by negative pi over 2 minus 1, which will leave us with dy over dx equals 1 over negative pi over 2 minus 1. So this is our answer. It doesn't look like any of the answer choices here are in the form of that. So let's just see what we can change with our answer to get in the form of either A, B, C, D, or E. Looks like we can start, maybe we can take a negative sign out of the bottom here. If we take a minus out of it, that would become negative 1 over pi over 2 plus 1. And then maybe we can multiply everything by 2. Multiply it by 2 over 2, which is just 1. So the top becomes 2. The bottom becomes pi plus 2, which is answer choice B. So that is implicit differentiation, just taking the derivative of every term standalone. And if you ever derive by a y, you multiply it by dy over dx. Then after that, you substitute every x and y with their values there, and then just solve for dy over dx.